Okay, so 101. So hopefully you guys are looking at 101 now. We basically have two blocks. There's B and there's A. And there's this surface here I call S. Okay, so what you want to do is draw two force diagrams, starting with the simplest one. Now, the question of the simplest one is not as obvious with these two blocks. I'm going to make my systems obviously the top block and the bottom block. So I'll have a system for A and a system for B. I'm going to begin with A. So if somebody wants to grab the... I'm going to begin with A. So with A, the bottom block, we have a force downwards. So that's the force of gravity on A from the Earth. We have a force, normal force from this bottom surface from S. So that's going to be perpendicular to the ramp. We'll call that FNAS. But then we also have another normal force because there's two surfaces in contact with A. There's this bottom surface, but there's also this top surface. So this top surface is also going to exert a perpendicular force, and that's going to be down like that. That's usually the one people neglect. So this would be NAB that points down like that. And block A is sliding down this ramp at a constant velocity. So it is moving, and there's relative motion between both of these surfaces. So both of these surfaces are going to exert a frictional force. So there's going to be a frictional force from the bottom surface, which I'll say FKAS. But there'll also be a frictional force from the top surface, from this surface right here. And that's another one that people usually neglect when they're drawing this out. So this is FKBS. Or sorry, it's FKAB. Alright, so those are all the forces on A. And there's no net force on A because it's moving at a constant velocity. And now we have to think about the forces on B. So we can draw a gravitational force down. So that would be FGBE. And the next thing we should do before anything else is recognizing that there's going to be force pairs here. This is going to have a force pair. This is FKAB, so there's got to be a force pair that goes like this and would be called FKBA. So that's a force pair. And here's another force pair, FNAB. It's going to have a force like this, and we'll call that FNBA. Alright, so don't forget about those, particularly the frictional forces. People almost always forget the force pair for frictional forces, including me. When I make a mistake, it's usually that. The next thing that I want to recognize is that there's also this string here, right? These forces alone wouldn't be enough to keep things from not moving on B's. The reason B's not moving is because there's a tensional force that points this way. So F, T, B from the string. Alright, so we've identified all the forces. And like I said, this is probably the most complicated of the problems that we'll see. Let's put some axes on these things. So there's an axis. There's an axis. So call this positive x and this positive y, positive x and this positive y. Alright, now this angle down here in the picture is given as 36.9 degrees, and that's the same as this angle here. And that's true for both pictures. They're both on that same incline. So, even though we have all these forces, we're lucky in one way, the fact that there's only two off-axis forces. So two that are at an angle that's not on just the positive x or the positive y axes. And that's the two gravitational forces coming off like that and like that. Okay, so now you have the rather tedious job of writing out the components for all these forces. I'll go ahead and do it, but it's going to take me a while. You can probably want to do it yourself and then check. So I'm going to start with A. AS is 0 Fn. You probably want to just do this on your own and then check with me. And I'll point out some mistakes that you may have made at the end. Oh, sorry, I'm making silly mistakes there. Sorry about that. A, B. Okay, so I'll pause here and talk about some of the stuff I did, some of the things I did. So, hopefully you recognize why these are the components of the gravitational force, because this x component is opposite, it points in the negative x direction. This y component is adjacent, it points in the negative y direction. Now you'll notice I did something with this normal force here that I didn't do with this normal force here. I gave this a new name. I just called it Fn. And if you're thinking ahead, you'll realize why I did that is because it's going to have the same magnitude as when I go over here and do it for B. And that later in the problem is going to allow me to make a substitution. Now, the other thing you have to recognize is that you don't get to just pick any normal force when you're doing these kinetic friction ones, right? The kinetic friction from the bottom surface is paired with the normal force from the bottom surface. And the kinetic friction from the top surface is paired with the normal force from the top surface. So there's a lot of notation here, but you have to understand why I chose to make all the steps I did. So after I get through this problem, I'll answer some questions about it. But if you have a question right now, go ahead and write yourself a note about it so you can remind yourself to ask it later, okay? So here I'll go do it for B. B's a little less complicated. So we have, another thing while I'm at it is notice I had to say M sub A, M sub A. Because there's two different masses, just calling something M isn't enough. You have to distinguish which M, because there's more than one. So I go over here, this will be FGBE, negative sine theta mbg negative cosine theta mbg, and I ran out of room for my bracket there, fk BA is going to be positive, or sorry, negative. Oh, that just shows me a mistake I made over here, right? Because these frictional forces are pointing in the positive directions, they shouldn't have negatives like that. My bad. All right. Because both of these forces are pointing in the positive direction. But this one points in the negative direction, so it will have a negative, sorry. So UK FN FTBS FT. And if this is incredibly tedious and boring to you, just go ahead and run ahead in the problem yourself and I'll catch up. All right. And then what other? I have to do the normal force. 0, Fn. Okay, so assuming I didn't make any other silly mistakes here, those are all the components. Okay. So now what we're going to do is write out the equations for both of these, and this is going to be a bit of switching back and forth. So what I'm going to do is for A, I'm going to think about the sum of the forces in the x direction on A and the sum of the forces in the y direction on A. Alright, so switching back here, if I want to know the x direction on A, I just add up all the x components. You should have this in front of you if you did the problem. So this is going to be UK FM, oops, minus sine theta MAG plus UK FNAS equals 0. So that's all the components on that guy. And the y direction, we have FNAS minus MAG cosine theta minus Fn. Okay, now we can do the same thing. So this is for A, so I'll kind of box this out. We can do the same thing for B, but because I've done this problem before, I know that we only actually need to know about the y direction on B, so to save a little bit of time, I'll just do the y direction. But you can obviously do both. It'll just be information that you're not going to use. So because I've done this problem before, I know that this isn't going to be any extra information for me. So I'm just going to do this one. And for B, I know that it's positive Fn minus MBG cosine theta. And remember, theta this whole time is at 36.9 degrees. It's just easier to write theta than 36.9 degrees. Okay, so all that was, though it took a while, was just looking at these components. That's why writing out these components is a useful step. And you'll see why, even though it's tricky, I've done the renaming. Because if I've done the renaming of things that show up in both systems, it allows for substitutions. So for instance, I'm going to rewrite this and say that Fn equals MBG cosine theta. Well, that allows me to substitute this relationship, which is in terms of things I know, into right here and right here. Okay? So I'll go ahead and do that. So this top thing right here, this top equation right here becomes FNAS minus MAG cosine theta minus MB MB cosine MBG cosine theta equals 0. So that's just substituting that into there. And again, I'm going to pause for questions at the end, so if there's any step that you're not understanding, just write it down and you can ask me at the end. Just make a little note for yourself. And then I'm going to do the same thing where I substitute it into here. Okay, and then I also get another substitution if I rearrange this FNAS. So this will be positive MAG cosine theta plus MBG cosine theta. So I know I got lines scribbling all over the place, but hopefully you see at the end of that what I'm doing is just basically a series of substitutions. It's just a puzzle to think of what can I plug in terms of what I know, in terms of what I don't know, to eliminate the things I don't know. So anyway, this whole nasty junk, we go back to our XA, the sum of forces on XA. This becomes mu K, replacing this with this, MB G cosine theta minus sine theta MAG plus mu K, and then everything in here gets substituted like that. Okay, our pain is nearly at an end. All we have to do now is solve for mu K. So what I'm going to do is I'm going to take this, I'm going to copy it, I'm going to take it to our next slide, paste it. Okay, and we'll walk through the algebras how to solve for mu K. So the first thing you want to do is distribute mu K MBG cosine theta minus sine theta MAG plus, and then remember this mu K has to get distributed to both parts, and if there was a negative in front of this, that negative would also have to get distributed. Forgetting to distribute negatives is a really common mistake. So you have to be mindful. I mean, that's what makes these problems so hard, is you basically have to focus for 15 minutes to get through it. Okay. Well, we see one thing. I'm not sure if you recognize that, right? But this is exactly the same term as this. If I gave you x plus x, hopefully you could recognize, you could simplify that to 2x. So that's what I'll do next. I'll combine these two terms, and that will be minus sine theta MAG plus mu K MAG cosine theta plus 2 mu K MBG cosine theta equals 0. Okay, nearly at an end. What I need to do now is isolate. Remember, the problem is asking for mu K. So what I need to do now is isolate all the terms that have mu K on one side. So how do I get all the terms that have mu K on one side by themselves? I just dump this guy over to the other side. So that's going to become mu K MAG cosine theta plus 2 mu K MBG cosine theta equals sine theta MAG. And then hopefully you see the conclusion of this problem. I factor out a mu K. and then divide. What I'm not going to do here, but that you could do, is that there is a g in every term, so the g's do cancel out. You can basically factor out a g from the bottom. In fact, I dropped it here. This should have a g. There's a g in every term, so you can factor that out. But basically, you do this, you plug it all in your calculator, and you get 0.45. And for those of you who are panicking, like I said, this is by far the most tedious problem on the exam bank. It definitely takes the longest to solve. But I'll pause here, and I can answer any questions. So hold on, let me pause my recording. Okay, so 106. If you look at 106, there's a brick, a string, a weight, another string, and an angle here of 30 degrees. This is on a surface, this is not. Okay, so again, I'll make two systems. I'll call this one A, and I'll call this one B. So I can draw a little system diagram about both of those. And it doesn't matter really which system you begin with. You want to try to pick the easier one, but your definition of easy might not be the same as somebody else's. I'm going to go ahead and pick A, because to me that looks easier. So A it has force of gravity pointed down. I don't want that, I want this. A has a force of gravity pointed down, so that's F, G, A, E. It has a normal force pointed up, so that's F, N, A, and we'll just call this the table or whatever you want to call it. It has a tension pointed to the right, so this would be F, T, A, and you notice I'm going to have two strings. So I'll call this string 1, and I'll call this string 2 to keep myself in order. You can call them whatever you want. You can call them banana and apple. It doesn't matter, but you need to differentiate between the two. And then finally, why isn't this thing moving? A lot of people think, they look at this, they say, great, I did it, but it's not moving. And typically if something's not moving, you need to ask yourself, is there static friction or not? And there obviously has to be to get things to balance out. So let me redraw that. So this is F, static friction on A from the table. And the question is telling you something. If you read the question, it says it's talking about we don't want things to move. It's a question about pushing this static friction to a maximum. So it's if we're talking about a situation where things are barely held in place, you're talking about a situation where static friction is being pushed to a maximum. And that matters because if static friction is at a maximum, it has to do with something with the coefficient of static friction. Okay, B, we go over here. B has a gravitational force that points down. F, G, B, E. It has a tensional force. Now this tensional force is not a force pair. Let me say that again. It is not a force pair with this. They're the same size, and they even point in the opposite direction, but they're not a force pair. And that's easy to see from the notation because when I write this, I'm going to put FTB1. This is obviously not the switch of this. So these do have force pairs. The force pairs to these forces exist on the string itself, which we're not bothering to diagram because it doesn't tell us anything useful. But I just like to emphasize that point every time it comes up because it's a confusing concept. Okay, here this angle is 30 degrees, and here we can give this a new name, FT B from our second string. Okay, and neither of these are moving, so the net force on both is 0. You're always happy if that's the case because it makes things easier. I'm going to draw some axes here. I don't know why I made my axes so big, but, you know, stuck with it now. Positive y, positive x, and now we're down to the tedious part of renaming the components. And like I said, you're going to get a lot more out of it if you try it yourself and then look up at the end than just watching me do it. So why don't you try to write out the components of these two systems, and I'll do it too, and then we can compare. Oops, AE, FTA1. Here we get to a place where we are going to rename because we recognize these are ideal strings across two systems, so we'll give them the same name. That'll allow us to do substitution in a little bit. And because the static friction is being pushed to a maximum, and only because it's being pushed at a maximum, I can do this. It's important to recognize that unless it's being pushed at a maximum, you can't make this substitution from USFN. Okay, so we can look at that there. I can draw the components for this one, FTB1. Again, we're going to give it a new name, just calling it negative FT, because it shows up in both systems. 0, this is FGBE. 0, comma, negative MBG. And FTB2. And this would be cosine, and again I'll put theta where this is theta, just to save room writing. MBG, comma, sine theta, MBG. Okay, so we feel good about that. There's all our components. Again, I'll copy and paste them to the next slide. Okay. Yep.
Why is it cosine of MBG and not FT?
Could you say that again?
Why is it the cosine of MBG and not FT?
Why is it the cosine?
Why did they say cosine? Why did you put MBG and not FT?
Oh, yeah. I don't know why. That's wrong. Sorry. Because I wasn't thinking. That is the answer. Thank you. Yeah. It's a Saturday. Thank you for pointing that out. FTB2. FTB2. Okay. Very good. So what we want to do now is just sum the forces in both directions. So A, Y, sum of the forces, A, X, sum of the forces, BX, sum of the forces, BY. Okay. So I'm going to do this the tedious way. where we just add all these things up. And that's fine. So this is going to be Fn AT, the normal force on that, minus MAG equals 0. This is Ft minus mu S Fn AT. Okay, this is negative Ft plus cosine theta Ft B2 MBG plus sine theta Ft B2. Okay. Now you have to ask yourself, what is it actually asking for? If you read the question, 106 says, what is the maximum value for the weight if we want to keep... So when it's talking about the weight, it's talking about the MBG of the second system. It's talking about this, right? You should recognize that this is the weight of the second system. So you ask yourself, well, how do I get that? I would need to know this. How do I get that? Well, looking over here, I would need to know this. How do I get that? I would need to know, you can see the substitutions happening, right? I would need to know this, and then finally that comes there. So if you don't see that, just start substituting into things, right? Try to combine equations to simplify. So for instance, I can rearrange this and plug it in here. So I can say MAG equals FNAT. Plug that into here. I get FT minus mu S MAG. So that becomes FT. So you may use all the equations, you may not. This one we will end up using every single equation that we generate. Where does this go? Down along the line. 0 equals negative mu S MAG plus cosine theta FTBS. And we need another substitution. I'm actually going to go to the next screen because I'm running out of room. I don't know why it's not picking that up too. I'll just capture all this. I mean, this is really just tedious algebra. Okay. Okay, so let's rearrange this for, and there's a couple ways you can do this, but what I'm going to do is solve this guy in terms of and I'm sure half of you have the answer by now, and I apologize for boring you, but it takes me a while to write it all out. Okay, and then this will finally go here. Negative MBG, so close, plus sine theta. Substituting all this in, mu S MAG divided by cosine theta equals 0. Finally, one last line. What I have to do is add this to both sides, because remember, what we're looking for is a quantity MBG. That is the weight of the box. So I just move that over to this side. And then the solution of this, the value of this, is our answer. So has someone calculated it yet? What is it?
8.6.
Say what?
8.66.
8.66. I'm sure you guys finished that like 10 minutes before I did. I'm sorry. Okay. Let's not do another interactions problem for a while. I'll pause that here and we can ask any questions. We'll resume the recording. Okay, 125, it has something interesting. It has 2 stars. And they're not orbiting. You couldn't say that one star is orbiting another because they're of equal mass. They're orbiting around what's called a barycenter, or just some random point in space. Nothing's there. There's nothing special about it other than it's the center of mass of these 2 things. So the same thing happens with, say, the Earth and the Moon. It's incorrect in some ways to say that the Moon orbits the Earth because the Moon doesn't orbit the perfect center of the Earth. A more correct way of saying it would be saying the Earth and Moon orbit a mutual barycenter, which is much closer to the Earth than it is to the Moon, because the Earth is much more massive than it is the Moon. But when you have 2 things that are nearly identical masses, the barycenter is shifted way over here. So let me distinguish that this problem is very different from, say the Earth and the Moon, where the barycenter is not quite at the center of the Earth, but somewhere very near the center of the Earth, because this is so much more massive. Okay. But anyway, what does this have you do? Well, you have 2 equations here in universal gravitation. You have this guy. This is Newton's law of universal gravitation. And notice this d. This d, what does this d mean? This means the distance between the 2 masses. So in your picture here, if you had to draw the distance between the 2 masses, you would draw a line like this, where that is d. But then when you look at your equations for circular motion, and specifically we'll pick out the period one because this one's asking about a period, it doesn't have d. It has r. And r is the distance from the center of the circle it's making. So if I asked you to draw r on your diagram, you would not draw a line like this. You would draw a line like that. And this would be r. Now typically, think about how this is different from most problems. Because for most problems, if I asked you to draw D with, say, the Earth and the Moon, you would draw something like this. And then if I asked you to draw R, you would draw something like this. Right? Here, in most problems, there's usually one more object that is far more massive than the other. So that D and R is essentially the same. D is approximately R. That's not true here. D does not equal R. In fact, D is twice as big as R. So what you can do is you can think about one of these guys. So let's think about this guy. We'll just draw a force diagram on this. I didn't want to do that. Hold on. I want to do this. So we'll pick the right star. And we'll say this is the force of gravity on the right star from the left star. Okay? Then we ask, so that creates a net force, assuming we ignore all the other forces, saying that they're insignificant. That creates a net force that is essentially the exact same size as this. So we say Newton's second law, F equals ma. Specifically like this. So what are some of the forces in the radial or towards the center direction? It's just F, G, R, L. And both of these have substitutions, right? This can be substituted for Newton's law of universal gravitation, m d squared. And this can be substituted for this guy here. So the way we've defined it, this is little m and this is big M, which is confusing because they're same masses, but because we're taking this as perspective, this mass represents this guy here. So anyway, m's cancel out. And it's simply algebra to solve for t squared. So let me take this over to the next page. Okay, so I'll begin by multiplying both sides by t squared, gm over d squared. I'll do a little bit more algebra to get t squared further by itself. 4 pi squared r d squared. Now normally we would have called this r by now, because normally r is essentially the same as d, but you'll notice I'm not doing that there, because they're not essentially the same. And then you just simply take the square root and get that there. Okay? And if you plug in, has anyone done that yet? Does somebody have the answer? Okay, so it's the last answer. The period should be 1.09 times 10 to the 6 seconds. So the whole problem is to get you to think a little bit harder about the formulas in terms of what does D mean and what does R mean. R has to deal with the circle, where R is a radius of the circle. D has to deal with the position of two masses, where it is the distance between the two masses. So I'll pause there and see if anybody has any questions. So we're going to do 123. So 123 says that there's a star and there's a planet, and we can make the assumption that the star is much more massive than the planet. So they tell us a radius here, a radius of the orbit, which is 2 times 10 to the 11th meters. And they tell us this orbital speed, so this is some tangential velocity that has a magnitude of 24 kilometers per second. Okay, and the 123 asks, what if this radius was halved, basically, so that it's only 1 times 10 to the 11th meters? What would happen to the orbital speed? Okay, so what you need to do is first recognize the same thing, that it's going to be Fg equals some mass times the acceleration towards the center. Substituting this in for universal gravitation, and substituting this in for the magnitude of the radial acceleration in terms of speed, because speed is what the problem is interested in. Now here we are allowed to make the assumption that d is approximately r, because one of these objects is far more massive than the other. And again, it's approximation, it's not perfect. So g, m, these masses will cancel out because there's one in every term. R squared equals v squared over r. And I'm going to multiply both sides by r. So g m r equals v squared. I'm actually going to show you two ways you can solve this, okay? And then I'm going to take the square root to solve for this. And you say, Mr. Merrill, this is no use to me because I don't know the mass of the planet, right? But think about it. This is a proportion, right? I can think about what's going to happen is if I half this, what happens to this? Well, if I half this, then this whole side gets changed by a factor of 1/2 inside of a square root in a denominator. Right? Work that out in your calculator. You'll get a number. If you take the square root of 1 over 1 over 2, you'll get a number. In fact, it's the same as the square root of 2, right? Hopefully I'm not being dumb here. Okay. Yeah, so it's the same as the square root of 2. So you get 1.414. So what this is saying is that if you half this, the whole side gets 1.414 times bigger. Well, if you make this side 1.414 times bigger, what do you have to make this side to compensate? Right. So you take this speed, 24 kilometers per second, and you multiply it. And you get 33.8 kilometers per second, which is answer D there. Now, some of you are not comfortable with that reasoning, so let me show you another way. You recognize that all you need to do to solve this problem is to get mass, right? If I had big M, I could solve this problem. Well, simply make up your own new problem where you solve for big M. You have enough information here to do it. Do it. So start with this point. I'll copy this. Right? You have an unknown, but you have enough information to solve for that unknown. Okay, so use the original problem statement of R equaling 2 times 10 to the 11th meters and V equaling 24 kilometers per second to solve for M. There's several problems like this. You can either think of it in terms of ratios, which most people aren't very comfortable with, or you can think in terms of just solving for the unknown that it's not directly spelling out for you to find. So this is not a hard problem to solve for what big M is. You can solve for that, and I'll go ahead and do it for you if no one has already. So 1 times 10 to the 11th divided by 6.67 negative 11. I'll obviously give you the value of G on the test as well. So 1.727 times 10 to the 24. And then you can just take this value, I'm bad at circling, and use it to solve the problem you were stuck with before, with the new radius. And you should get the same number. Okay, so I'll go ahead and pause there. So 159 and 160 asks us to visualize a block going down a ramp. The block starts out at some height, and it ends up at the bottom of the ramp with some speed, some velocity, okay? But you'll notice if we try to draw an LOL diagram, or an energy bar diagram, and we include the Earth and the box in the diagram, then you'll see initially we start out with essentially just gravitational potential energy. Energy stored in the height or the current position of the box. And at the end, we're out of gravitational potential energy and we just have kinetic energy. But it's not as much, right? This is not as much as this. We're talking about 17.5 joules compared to 50 joules. So it doesn't add up, right? We don't have the same energy in the beginning as we do in the end. And so where'd that energy go? Can't just disappear. It means energy had to leave the system by some mechanism. Well, what was the mechanism? It was the mechanism of so there's a lot of forces here. The force of gravity. Well, we don't care about the force of gravity because the Earth's inside the system, it's internal. The normal force, well, we don't care about the normal force because it's perpendicular to the direction of motion. There's no component. But there's friction. And this friction points in the parallel to the direction of motion. It's opposite. Points backwards, but it's still parallel. And it's applied over some distance. So that's going to remove energy. It's going to subtract out energy. So we can think about the work done by the non-conservative force of kinetic friction. And we don't need to know the magnitude of the force or the distance applied over if we want to find the work done. The work done is simply equal to the energy transferred. So if we start out with 50 joules and we end up with 17.5 joules and we want to calculate the energy transferred, how would you do that? You just do the final minus the initial. Right? That's what change is, final minus initial. So 17.5 joules minus 50 joules is negative, because we're going down, negative 32.5 joules. So let's just say, start out with 50 joules, remove negative 13.5 joules, and you'll have 17.5 joules. So what it's saying, number 59, approximately what is the work done by friction, there you go. Now 160, what does 160 ask for? It says, what is the average power delivered by that frictional force? And you get this rather complicated equation. But if you're stuck, then you're looking at just what the equation has written down, and you're not thinking about what the equation means. Because what is this? This is work. This top part is the energy transferred per the time it takes to transfer it. We already know what this top part is. This top part is that negative 32.5 joules. And the time to take for transfer it is just the time that this process took place over. So 1.25 seconds. And if you do that, I'm going to guess, because none of the other numbers are close, that you get negative 26 watts, or negative 26 joules per second of energy are transferred out of the system on average. Now, where did the most of the energy transfer take place? It took place more at the end than at the beginning, because it was covering more distance towards the end than it was at the beginning. Okay, so I'm going to pause there. So 157, we have this block on a table and it's compressing a spring, and then we let the block go. It's going to shoot off the end of the table and act as like a projectile, and then it's going to get to the ground with some speed. And the question asks, what is that speed? So this line here at the floor we'll call h equals 0. Alright, so we'll call that h equals 0, and then a good place to start is to think with the energy bar diagram, or more lovingly referred to as the Lowell diagram. So we have Earth, box, and we want to think about the energy that's being stored here. So I think the first thing that people think of is the spring energy, and that's fine. So E, L elastic. But if I want to store energy as a spring, I'm forgetting something over here, right? If I want to store energy in the spring, I need to include the spring as a part of my system. Alright, so we have elastic energy stored in here, but we're storing energy in some other way as well. We're storing some energy in the height of the table here. We're storing energy in the position of the box in the Earth, or as gravitational potential energy. But then we have to think about the forces that act on the box. Well, there's going to be a normal force up, a gravitational force down, a spring force that pushes it forward, and a frictional force that pushes it back. So you can't really see my frictional force, but my frictional force that pushes back. So we don't care about the gravitational force because it's internal inside of the system. We don't care about the spring force because it's internal, it's inside of the system. And we don't care about the normal force because it's perpendicular to the direction of motion. But as the box moves to the left, the friction acts to the right, and that's going to remove energy from the system. That's a working process that removes energy. So we're going to have some energy going out, WNCK. You would not have this arrow on question 156 because 156 tells us to ignore the friction. So we have that being moved out. And then so altogether we have a little less energy in the end. We went from 2 blocks, we took out a block, so we only have 1 block. And now the energy is all being stored as kinetic energy as it reaches the ground. So we can set up an equation. We say EL plus EG plus WNC, the energy transferred by the force of kinetic friction, equals EK. We can make some substitutions here, but first let's think about what this is going to be. Because this is the only one that's not directly spelled out to be the same every time we plug it in. So work done by a force is equal to the plus or minus the parallel component times the distance. Well, for friction, it's in the opposite direction of motion, so that's negative. That should be pretty obvious. And then we have to think about the parallel component. Well, all of the friction is parallel to the motion, so we get to put all of Fk there. And then what's the distance? Well, the distance is something else in the problem. It's it's x basically. It's this 0.1 meters because that's the entire time it's on the surface there. So that's kind of special to this problem. Now you can get it from a force diagram, but I'm hoping this far in the year you can recognize that this Fk is mu k m g. That the normal force has to be equal to the force of gravity mg, and the Fk is simply the coefficient times that, and that altogether gives us our non-conservative work done by friction. So that'll go there. We know what the rest should be: 1/2 k x squared plus mgh uk mgx equals 1/2 mv squared. And we essentially have a little bit of algebra, so multiply both sides by 2. It saddens me deeply when students aren't sure how to finish off this algebra. So let's go ahead and practice. Of course, we don't need to. We can leave it undistributed in our calculator, but let's just go ahead and distribute it. The 2 goes to every term. And we can divide both sides by m. So instead of writing out another line, oh, I didn't want to do that. It's a big mistake. Divide both sides by m. That cancels out the m on the right. Get a little m there. And then we can take the square root of both sides. And then you plug in. And if I remember correctly, the answer is 7.63 meters per second. And we can do a sanity check, because if you did the last problem correctly, you realize that the last problem had an answer of 7.7 meters per second. So obviously if there's friction, I'm hoping you can eliminate answers D and E from 157. Adding friction to that table is not going to make things faster when it hits the ground. It's going to make things less fast. So this answer makes a good bit of sense, because the idea is applied over such a short distance, we're not removing a whole lot of energy. We're removing a little, so that affects the speed just a little. So I'll pause here. Okay, so it's asking for how much time it takes to reach this point. So it's only the initial point and this point that we concern ourselves with. This is basically our I, and this is our F. Blind yourself to everything else. Doesn't matter. So we make a. If you watch my videos that are on the exam section, they go over a very similar problem, so you might want to do that as well. But what you want to do is basically make a diagram like this, where you think about all the possible things that could possibly matter. And there's really not a whole lot. There's the velocity and displacement in the x direction. There's the displacement in the y direction. There's the initial velocity in the y direction. There's the final velocity in the y direction, the acceleration, and the time. So 7 things, assuming I haven't forgotten any, which I don't think I have. So you can just remember that's 2, 4, 1. And this diagram will help you out a lot. So what it's asking for is this. That's the time. And what you should do first with a problem like this is, if it's a problem where the initial velocity is an angle and you're given the speed and the angle, go ahead and dissect that up. What I'm saying is find the components. So this is Vx and this is VIY. So how do you find this? You do 15 sine of 60. And how would you do this? You do 15 cosine of 60. So I believe this would be 7.5 meters per second. not as sure about this because you have to multiply by some weird square root. So times cosine 60. Nope, backwards. Shame on me, not remembering my basic trig. So 7.5 meters per second. 15 times sine 60. And this is the 12.9. Okay. And a lot of people, I've gotten this problem several times. They say, how do I know whether to make this positive or negative? You just look. Does it go up or down, right? You can assign it. I mean, I don't do this. I really should. But you can assign a coordinate axis to this whole thing. This is positive x. This is positive y. So things that point up are positive. Things that point down are negative. Things that point right are positive. Things that point left are negative. And most times, things start out positive because most projectiles you fire up in the air. But you've seen problems when they like roll off a cliff or slant a table and you get a negative Fy, or things that are fired from right to left where you get a negative Fx. It's not a big deal. Just put the negative there. All right, so this is 7.5 meters per second. This is 12.99 meters per second. Now, most people can do that. What they struggle with is getting the things that are not directly spelled out. So the first one that should be obvious to you is negative 9.8 meters per second squared. And why is this? Because the acceleration of a projectile in the y direction is just equal to the negative of the strength of gravity. So g is just a number 9.8 meters per second, and negative tells us that it's pointed down. The other one, which is the key to this problem, is recognizing that here at the top, that is not what I wanted, here at the top, the velocity is going to be like that. And what you can recognize, and it's useful to draw the velocity arrow here if you don't already. It's useful to draw that because what you recognize is that there can't be any final y velocity. So this is not something that's spelled out in the problem. It's something you have to recognize as zero. Now, when you're doing this, we don't know these things either, right? Because I don't know how high this is. I can find it out, but it doesn't directly tell me. And I don't know how far this is over. Again, I can find it out, but it doesn't directly tell me. So I don't know these things, but I don't need to know these things. So what you do next is you look at your equations for kinematics and you ask yourselves which are the most useful out of this problem. And the best way to do it is just practice, because without even looking at the equations, if you do enough problems, you'll realize that, hey, there's a pattern here. I've done problems like this before. I want to use this equation. And in hindsight, it's obvious why you want to use this equation. No, it's not. You don't want to use this equation. I lied. Two mistakes in one problem. That's over my quota. All right, you want to use this equation. I apologize. Fy plus at. You want to use this equation. Why do you want to use this? Because you know this, you know this, you know this, and you want to know this. So that means we have our one unknown, but everything else is known. If we had gone with any of the other two equations, you'd basically be stuck needing to know delta y, which we don't have. So now we can just rearrange Vf. Well, this is 0. So rearranging, this is just going to be negative Viy divided by Ay equals t. So 12.99 divided by negative 9.8. The negatives cancel out, and you get a time of 1.325 seconds. So that tells me there's an issue because that's rounded incorrectly, because it looks like the key gives it as 1.324. So I apologize for that mistake. I'll fix the key to fix that rounding issue. Okay. So I'll go ahead and pause there. Okay. So for 93, it's kind of this, we have an infinite pit here. And it's saying I drop a ball, and I'll say that happens at t equals 0 seconds, and then I'll pick a different color. I drop another ball at t equals 1 second. Okay? So what I'm going to do is show this black ball for all points in time, at least for a couple seconds, I should say. So it's going to start out, the next second it'll be kind of far apart. But what's the problem with putting second 2 right here? What's the issue with that? That's saying that it's falling at a constant velocity, right? This doesn't make any sense, right? This is saying that it's falling at a constant velocity, but things don't fall at a constant velocity, they accelerate. So the next gap here should be bigger. And the gap after that should be even bigger. Right? For something that is accelerating, the distance it covers with each successive second increases. Okay? So that, and this follows what's called the odd number rule. So whatever spacing that is here, which is, it would actually be 4.9 meters, the next spacing will be 3 times as big, and the next spacing will be 5 times as big as that original distance, and the next one will be 7 times as big. But anyway, what you need to know to understand it is that it simply increases, that it's not constant velocity. The spacing isn't even. So what we're going to do for this is, remember, here it is at 1 second. Okay? For the red ball at 2 seconds, it's here. For the red ball at 3 seconds, it's here. For the red ball at 4 seconds, it doesn't matter because we don't have any 4 second to compare it to. But what I want you to look at is, at 1 second, what is the spacing? Right? At 1 second, how far are they apart? They're about this far apart. Right? Here's this guy. Here's this guy. It's at 1 second. At 2 seconds, what is the spacing? It's like this. That's the separation between the balls 2 seconds later. At 3 seconds, what is the spacing? It's like this. It gets bigger. And it makes sense because you have to imagine this as basically the shadow, the 1 second delay behind this guy. And if I just said that the spacing increases with each second, that means that the spacing increases with each second, with the second ball representing that, the red ball representing the previous position. So this pattern will continue to increase like that. What's another way you can recognize it? You can think about and this is a little more abstract, so I don't know how helpful it'll be, but you can think about a velocity versus time curve. So the the black ball, and let me use a line so I don't screw this up. The black ball's velocity will increase linearly, meaning its speed will jump up by 9.8 meters per second every second. So it'll go from 9.8 meters per second at 1, and it'll go to negative 19.6 meters per second at 2, and so on and so on. Right? So it's linear like that, right? The velocity is linear, but you'll see in a second that the displacement or the distance is quadratic. So what is the red ball doing? Well, the red ball doesn't do anything for that first second, and then it begins to follow that same curve because it has the same acceleration. So let me show that. At 1 second, it does something like this. They both have the same slope, right? They both have the same slope because they both have the same acceleration. Now, without a grid here, it's going to be a little bit hard to explain, so I'm not sure how far I'll go into that. But basically what you can do is you can shade in the area under the curve, which represents the displacement. So let's look at how big the triangle is for the first second for the black ball. It's about this big. And if you actually calculate that area, it's 4.9 meters. And the next second, it's this area plus the previous area. And if you calculate that distance, it's something like 19.6 meters, where this guy is only 4.9. Calculate the next second. This area is everything previously, where this is only this guy here. So if you look at the rate those two triangles grow, as you go to the right, this big triangle becomes a larger and larger ratio compared to the smaller triangle. And I don't know how helpful that is, but I just figured I'd explain it in a different way than this. And if all F fails, just make up numbers and calculate it. Right? Get out a kinematics equation and actually calculate a couple of the displacements at a couple different times. And you'll find that the kinematics equations say exactly the same thing. That this one grows with a bigger jump in each second of time. So I'll go to pause there for questions. Okay, so this is, let me remind myself, problem number 87. It has a car going through a dip, and the question is, what is the current speed at the bottom? And it gives me information about my weight, and this little tidbit about 3 times greater than you experience. Okay, so first of all, let's, because this is still an issue for a lot of people, Fg equals mg, right? This right here is weight, meaning this altogether is weight. Just m is mass. So all too often I'll see people solve the problem and they'll plug in 850 newtons for the mass. That doesn't make any sense. 850 newtons, that's a unit of force. It's trying to tell you what Fg is, trying to tell you what mg together is. So make sure you understand the difference of that. And then separately, Fn, which you know as the normal force, also has the definition of being an apparent weight. Because it is the weight that you experience. Right? Your actual mass and strength of gravity doesn't really change on a second-by-second basis. But if you're going on a roller coaster and you're going up and down in hills, you feel heavier and lighter. Not because Fg is changing, but because the normal force is changing. Basically, the push on your butt is changing. You are experiencing a different force. All right, so let's think about this guy here. Now, again, this is the way the notation I use here is going to be different than the notation that Dr. Holt uses. You should get the same answer either way. Okay, but actually here it won't make a very big difference at all because towards the center of the circle is up. But yeah, it's going to be different. Okay, so we think about two forces on us in the car. So we're in the car. We have a force of gravity that points down. Right, a force of gravity that points down, and that's on you. It's from the Earth. And then we have a normal force that's on you from whatever seat you're sitting in. Okay? And why did I make this bigger than this? Because I had to recognize that there's a circle here, or at least a part of the circle, where the center of the circle is currently at the bottom directly above us. So the center of the circle is here. Now here's the part where I use some notation that Dr. Holt probably does not use. That's okay, you'll still get the same answer, but it just might not make sense to you what I'm doing. I'm going to call this direction the positive R direction. So this is a positive R axis where Dr. Holt would call it a positive Y. So anyway, let's sum our forces. So that these two forces produce a net force that points towards the center of the circle, and you should always have that. If you don't have a net force pointing towards the center of the circle, or at least with a component that points towards the center of the circle, then you can't change direction. So we sum the forces, set them equal to the mass times the acceleration. So this is an acceleration that points towards the center of the circle, and this is a net force that points towards the center of the circle. So first we need the components. And again, this is where it's going to really bother you if you're in Dr. Halt's class, because I'm going to use different notation. So in my notation, I say it's the R component, then the Z component. So when I write out these things, they're going to look different. Sorry. So NYS, I'm going to write it as positive Fn. Yeah, I know it's in the first slot, but I'm making a new axis called the R axis, and this is the R direction. And this is FGYE, and this is going to be negative mg. So if you're in Dr. Halt's class, you'd say, why is he putting him there? I just put him there. That's fine, I don't care. But then I go over here and sum the forces. This is going to be Fn minus mg equals MAR. Now, now we get to the point where we have to substitute this AR for something. The whole problem is talking about speed, so we'll make the substitution that Fn minus mg equals mv squared over r. And you get to this point where you say, I could solve this, but I don't have Fn. Yeah, you don't directly have Fn, but I give you some information. I say that Fn is 3 times greater than what you're used to experiencing. Well, in your everyday life, how do you think Fn compares to Fg? Like right now in your seat, how does Fn compare to Fg? If you're not accelerating, these two are equal. And I tell you that this is 850 newtons. I tell you your weight is 850 newtons, so you're used to experiencing an apparent weight of 850 newtons. So if I'm telling you if it's 3 times greater than that, I'm telling you that Fn is equal to 3 times 850 newtons. All right, so we solve for speed. So multiply both sides by r. Divide both sides by m. Square root both sides. And plug in all these values. So r is 25 meters. Mg, you say, oh, I don't know the mass. Yes, you do. Yes, you do. Right? Because Fg is equal to mg. So you can easily find the mass. Just take that 850 newtons and divide by g, and you have your mass. Okay? So do that. Plug all that in. Go ahead and try it yourself now. I'll do the same, and we'll see what we get. So I get 22.13. So hopefully that's the answer keyed in. So I'll pause there. I'll give you guys... Okay. So here we have 102 and 103. And it's a rather long problem statement. I give you a bunch of things. But the main thing you have to recognize is that we are moving up this ramp at a constant velocity. And you might be a little bothered by the fact that you're not given this angle, but take a deep breath. It's a very easy problem to find that angle. So let's do that first. So the tangent of that angle has to equal 2.5 divided by 4.75. So to find the angle, you can take the inverse tangent, 2.5 divided by 4.75. So do that very quickly. Make sure your calculator's in degree mode. And I get 27.75 9 with a little bit of rounding. Okay, so I'll just refer to that angle as theta for the rest of the problem. Now, the point of 102 is namely to make you recognize that Fs does not equal, necessarily, it does not have to equal mu s Fn every time. I know, some of you are freaking out, but what you're forgetting is that Fs equals at a maximum mu s Fn. This has to be true, right? Because otherwise there would be some fixed value for the force of static friction every single time. But just think about pushing a block, right? Just think about a block on a flat surface. If I push it with a force of 5 newtons and it doesn't move, how big is static friction? It's pushing back with a force of 5 newtons. But then I could take that same block and push it with a force of 6 newtons. It still doesn't move. So how big does static friction have to be? 6 newtons, right? It's allowed to be different values. All this tells you is how big it can be until it slips. So the idea is that if I push it with exactly 7 newtons of force and it just begins to slip, like you can feel it give, then you push the static friction to a maximum at 7 newtons. So there's a difference, right? So a lot of times what people think this problem is they think this problem is finding what Fn is and then multiplying by the mu s I give you in the problem. I'm actually tricky, and I apologize, that the mu s you never end up using. Even though I'm asking for the force of static friction, for this problem, the force of static friction is not being pushed to a maximum. So that mu s is irrelevant because that mu s only matters when static friction is at a maximum. So what you do is you draw the force diagram for this top box. You draw the force diagram for this top box. So this is FG, let's just call this A, doesn't matter. AE. Fn, we'll call this down box B. B, it should be AB. And then you say, I have no idea which way to put static friction. I don't know where to put it. Does it go down the ramp? Does it go up the ramp? But then you have to realize that I'm moving at a constant velocity. So which way does it have to go if the box is moving at a constant velocity? It must point up the ramp. Otherwise, things wouldn't balance out, right? So this is Fs AB. Okay, and then I can draw some axes. Oh, don't want that. Way too big. I can draw an axis like that, an axis like that. Try that again. I'll call this positive x. I'll call this positive y. And if this angle down here is theta, this angle here has to be theta. So G will have some components, some x and y components. So this is actually, once you realize that little trick, that mu s is not, that the static friction is not necessarily at a maximum, I really don't have to do a whole lot to solve this problem. Because what does this have to equal if it's moving at a constant velocity? It's to equal this, right? These two have to balance. They're the only two in the x direction. So yeah, you can do the components and you can write out all the stuff, but be clever. Recognize that FSAB has to equal MAG sine theta. Otherwise, it wouldn't be moving at a constant velocity if these two weren't the same size. So that's a rather easy calculation. So this is 32 kilograms. times 9.8 newtons per kilogram times sine of that 27.759 degree angle. Notice that nowhere did I use mu s because the problem isn't talking about pushing that to a max. So you do that, and I don't remember what you get. I think 146 if I remember, but oh, all right. FSAB. Okay, and now the next problem also seems challenging, but it's rather simple to do if you're clever about your choice of system. So let's move to the next problem. So the next problem is asking, what does this pole have to be? And all too often, because you get so used to each box has to be a system, each box has to be a system, each box has to be a system. And sometimes that's the case. In fact, a lot of times it is if you want to solve the problem. But ask yourselves, is there any way I can get away with just picking one system? And here I will. I'm just going to make this all one system. I'm going to make both of these blocks one system. I'm just going to pretend like they're all the same junk together, okay? So that changes one thing. I have to realize that now when I'm talking about M, it is the combination of 32 kilograms plus 48 kilograms. Because if I'm putting everything in one system, then the total system mass is bigger than it was. Now, I don't want you to think, if you don't like doing it this way, be my guest to make two separate systems and go through all the algebra of that. It's much more difficult. I'm not going to do that. But now we can think about forces acting on this system, just this single system. So this is FG, and we can call it whatever you want. I hesitate to call it A because I called the last thing A, so let's not do that. Let's give it a new name. I don't know. Z. Don't get to use that too much. So the force of gravity on Z from the Earth, you can call it whatever you want. I don't know. It has this normal force that points at an angle. So Fn acting on our system, what I'm calling Z, from the surface or the ramp or whatever you want to say. I'll just call this R, ramp. And I'm pretty sure I said this bottom thing is frictionless, right? No, I mean I put friction on this bottom surface, so we got to deal with that. So there's friction on this bottom surface, so Fk and then Ft, or pole, I guess I called it in the problem, pole Z R. So if you're pretty good at these diagrams, you kind of already see what's going to happen. That the pole has to equal the friction plus the x component of gravity. Again, I'll call this positive x and this positive y. So this angle here is the same theta as last time. I don't even remember the number, 22 something. And then theta right there. So you have to work through the stuff. You have to write out the components and set up the stuff. So I'll go ahead and do that. We've done it before, but let's just practice. So Fn ZR. Here, since we're dealing with one system, we can just call things more simplified names. F pole. Yep. Again, this component is going to be negative because it points down the ramp, so negative mg sine theta, comma, negative cosine theta, mg. I don't know why I switched that. Obviously, the order of multiplication doesn't matter. And then, what am I missing? Fk. So FKZR. This problem is also similar to, if I can find it very quickly, I think it's towards the beginning. It's also similar to that one where there's 3 boxes or so, number 20, or sorry, 21. 21 is also very simple if you choose just one system, so this would be a good problem to follow it up with on your own. So this is negative mu k Fn, comma 0, and then, and then we'll take all this, we'll copy it over, and we'll work out the algebra. And I'm guessing at this point probably half of you are done already. I don't know why I'm so slow. Got to write. All right. So x equals 0. Sum of the forces in the y equals 0. The one nice thing about this problem is that it's constant velocity. So F pole minus mg sine theta minus mu k Fn for the x's, and then for the y's, Fn minus cosine theta mg equals 0. Hopefully you can see the substitution. Cosine theta mg. This gets substituted into here. F pole minus mg sine theta minus mu k cosine theta mg equals 0. Move these two things over to the other side. You get F pole equals mg sine theta plus uk cosine theta mg. And has somebody calculated that yet? Has anyone calculated it yet? I guess I'll calculate it. So remember, the total mass is 80 kilograms. And theta, I think we found to be 27.759 degrees. So putting that all together, times sine, mu k from the problem statement is 0.44. So plug that in too. So just cosine times 80 times 9.8. I screwed something up. Give me a second. Times sine 27.59. Alright, so I'm getting a number that's far too big.
I got 670.
673. Okay, so let's see if I made a mistake. Did check my algebra. There could be an issue with the problem. I have not worked this problem previously. Oh, do you think? Oh, so that I must have, when I first worked it, screwed up. I probably had this as a negative, I'm guessing. But you can see simply from the diagram, it has to be the sum of both of these, right? Both of these added have to equal this. So I'm fairly confident. I'll double check it on my own later, just to make sure I'm not, because it's kind of hard to think when you're talking. Times cosine 22.759. But yeah, I'm getting, so that's likely an issue. When I first solved it, I made this a negative here, so I'll fix that for the exam bank. So that should be 0.1 newtons. So this is number 103. Apologize. Oh, yep. I had the angle wrong there. So 27.5. Yep, that's dyslexia there. Okay, yeah. Sorry about that. Okay, so you got 670 what?
673.
Okay. That's what I got. Sorry about that. Okay, so I'll fix that on the test options there. Okay, so let's go ahead and pause there. So we have to understand what this is. This is 95. We're looking at a y versus x. So this is basically showing the actual trajectory, their actual path. Basically, if you can imagine a time-lapse picture of the two projectiles. So this is the actual path. So the first one says the y component of B's initial velocity vector is equal to the y component of A's. So that's a very dense statement. But what you have to realize is that the y component of V tells you two things. It tells you flight time, and it tells you max height, assuming they both have the same initial firing position. Obviously, it can move one cannon 10,000 feet in the year, and that's going to change things. But assuming they're both fired from the same position, then the initial y velocity determines these two things. So I can't see time from a y versus x graph. There's no time on this graph. But what I can see on this graph is what? I can see the maximum height. So so this is A, I'm not sure how well this is labeled, but this is A and this is B. And A does not reach the same maximum height as B. So before anything else, I know something about the y components. Whoops. I know that B's y component has to be greater than A's y component. Right? And how do I know that? It's based on the fact that it had the maximum height. So this is the by component, and this is the so VIY for B, and this is VIY for A. So this cannot be true. If they don't have the same max height, then they don't have the same y component. Now, let's come back to B. This is probably the most difficult. Let's look at D. The answer depends on the mass of the two projectiles. No, mass never affects projectile motion because the only force is a force of gravity, and if your only force is a force of gravity, then the additional mass is canceled by the additional resistance to mass, or the additional resistance acceleration. So it's not D. C says the y component of B's initial velocity vector is more than doubles. So basically we're down to these two choices, right? Figuring out these two. And there's a couple ways to figure this out, but what I want you to realize is that for either one, the final y velocity at the top is 0. Now let me say that again. The final y velocity at the top is 0, not the final velocity in general. Right? These things are still moving at the top, but their velocity is purely in the x direction. So we have an equation that we can think about. V Fy squared equals 2a delta y. What am I doing? This is what happens when you do too much physics on a Saturday. So VFY squared plus 2a delta y. So why am I looking at this equation? Well, what I can do is I can say, okay, this first part is 0. And then I can rearrange basically for VIY. I can rearrange for this. So I feel like I'm running out of space. No, I don't want to take that. Scoop this out of the way. Okay, so I got to do some algebra here. So move this to the other, move this junk to the other side and square root it. So this is going to be negative 2a delta y square root equals VIY. So that's basically rearranging this. Now, what you can see from the grid is that delta y for b is double that of a. So what you got to ask yourself, does doubling delta y double this? And the answer is no. Right? Again, this is visually hard to see, but plug this in here, right? Plug this in here. You put a 2 in here, but what are you then doing to that 2? You're square rooting it. So by doubling the height, you only square root of 2 the initial velocity. So this isn't twice as big as this. It's only the square root of 2 as big as this. Alright, so that's one way to think about it. But that's usually pretty difficult for people. So what's another way to think about it? You can, again, just like the last time we encountered this, make up numbers. So I don't know what this is, and I don't know what this is. But can I make up numbers? Sure. Let's just call this 100 meters and call this 50 meters. Solve for VIY in both of those cases. So plug in 100 meters. Negative 2 times negative 9.8 times 100. You get a velocity of 44.27. Now try it again for 50. 2 times 9.8 times 50 square root. You get 31.30 meters per second. So yes, this is bigger, but is it twice as big? No. So it's not double. So the answer is C. Specifically, it's not double, it's a factor of the square root of 2. So a lot of these conceptual problems, even though you feel like you have no information, just make up your own numbers. Right? If numbers help you think about it. So you can do that for this, you can do this for the dropping ball problem, you can do it for pretty much any of them, just make up numbers. And as long as you follow logical steps, then you'll get the same answer. So let me pause there. Okay, so two spheres of equal mass, not that that matters, are projected horizontally, so this is number 96, are projected horizontally off the edge of the table. Sphere A has twice the horizontal velocity of sphere B. It's saying that sphere A hit the floor right here, and the question is, where does sphere B hit? So the first thing you have to recognize, the hidden part of this, is that it would actually be easier to answer 97 first. Because if you can get 97, it's very obvious why 96 has to be the way it is. So 97 says ball B takes exactly 1 second to hit the ground. So it follows some trajectory and it takes 1 second to hit the ground. So you ask yourself, why is the answer this? Why is ball A also take exactly 1 second to hit the ground? Well, as stated earlier, there's a couple ways to think about it. The simplest kind of back of the rule to think about is that if the y velocity determines max height and flight time given the same initial position, which they have, then they have the same initial y velocity. Not the same initial velocity, but the same initial y velocity. They both have an initial y velocity of what? Of 0, right? So if they have the same initial y velocity, then they must have the same flight time. This is the same problem as a previous problem where you project one off the table and you simply drop one, and they both take the same amount of time to hit the ground. That's because if you look at, that's because they're accelerating in the y direction at the same rate. So their distance in the y direction is changing at the exact same rate. And their distance in the y direction is going to determine when they hit the ground. All the x direction does is say how far to the right you go for that time you're in the air. But given the same initial velocity and given the same position, they will hit the ground at the same time. So both of them hit the ground at the same time. So now if we go back to 96, and B has, again, here's one where you can just make up your own numbers. B has an initial velocity of 5 meters per second. A has an initial velocity of 10 meters per second. Why not? The only condition is that it's doubled, right? So if A was moving at 10 meters per second for 1 second, how far away did it hit the ground? All right, it hit the ground 10 meters away. Right. All right, and then now it's very simple to see that for something that's moving with an initial horizontal speed of 5 meters per second is in the air for 1 second, then that only moved 5 meters. So exactly halfway. Okay. So that's probably the simplest way to think about it. Struggling to think of another way. I mean, you can just totally make up numbers for the whole problem. You can make up a height here, call this height 10 meters. You know, you can do whatever you want. But the idea is that the horizontal velocity just tells you how far you go to the right for every second that you're in the air. So if you're in the air for the same amount of time, then it's just multiplying the two, and the one that's moving twice as fast moves twice as far. So I'll go ahead and pause there. Resume. So two planets orbit a star in circular orbits. The planet that is farther away from the star. Okay, so let's think about this. Here's our sun. Here's planet 1. Here's planet 2. We don't actually know how much farther. It's not necessarily double or anything like that. But we just know they're orbiting in circles, and planet 2 is farther out. So if you really want to think about it, you have to think about it in terms of this. Gm over d squared equals g, and then a, you can either think about it as v squared over r, and okay. So let's eliminate the craziest one first. A larger universal gravitational constant. Absolutely not. Big G is the same for everything, so you should give that one no thought. Now, the other things you can kind of think about, first of all, before we get to this, I mean, if you have some basic background knowledge of our solar system, just think of the outside planets, right? You've heard things like Pluto takes way longer to orbit around the sun than the Earth does. So the more distant planet should have a greater period and stuff like that. But we can go ahead and get it from the equations too. But I'm saying don't be so wrapped up in the equations that you throw away logic if you find something else that points out you made a mistake somewhere. All right, so let's see how radius is related to these two things. Let's first see how radius is related to period. So it's saying that if the only force acting on you is gravity, then G equals the magnitude of AR. Okay? So we can set these things equal to each other, GMD squared, 4 pi squared over T squared. And we can make the assumption that these planets are not nearly as massive as the stars, so this R, or this D squared can be approximated as R squared. We talked about that with an earlier problem. So what we want to do is set up an equation for period that depends only on radius. So that involves a little bit of algebra. Multiply T squared on both sides. Multiply R squared on both sides. And divide it by GM. So I'm skipping some steps here, but I'm confident that if you take your time, you'll arrive at the same thing. And then square root it. Okay. Now we don't have any numbers here, but make them up if you want to. Like I said, at any point in time you can make them up. If you want to make up a mass of the sun and make up two radiuses, as long as this radius is bigger than the other, you haven't violated anything, right? But anyway, hopefully it's easy to see this as a function, whereas r gets bigger, what happens to t? It gets bigger, right? Plug in a bigger number in the numerator here, this gets bigger. If you're not comfortable with that, just make up your own numbers and see it, right? So this must have a bigger period. Okay? And say an easy way, I'm not saying that I would, but I'm saying an easy way that I could change this problem is change period to speed. How would you do that? Just go back to the same starting point. Instead of using this, you can say v squared over r, do the same little bit of algebra, and now I ask the same question. If I make this bigger, what happens to this? If you're not sure, just make up two sets of numbers and plug in. But if you make this bigger, you make the denominator bigger, so you're dividing by a bigger number, so this side becomes smaller. So as this increases, this decreases. So this one would have the lower speed and the bigger period.
So then how come D and B are correct?
So what?
Then how come, because it says lower speed too.
Oh, the planet that is farther away. Oh, yeah, I see what you mean. Yeah. So is that a mistake? Let me make sure I didn't do anything silly first. It could just be a mistake with the key. But let me make sure I just didn't do anything silly first. So bigger, lower speed, greater period. Okay, so yeah, that's just a mistake, right? What this should have said is the one that is closer away, I'm guessing, or closer to it. What does the actual key have it as? If someone could check. B, okay.
So then should D say something else?
Yeah, D should say something like greater speed. So I'll fix that. And the fact that it's, usually if there's a mistake, I will make it exceedingly obvious that it was a mistake if I use any form of it on the exam. I'll basically eliminate that option so there's no way to get confused.
Bless you.
So thank you for pointing that out. I didn't realize that, but yeah, hopefully that makes sense how you see how I got there. So yes, this outer planet has the lower speed and the greater period. Okay, any other, so somebody said 90 and 91, so I'll go and pause there. Okay, so this is a very similar problem to the last one we did. Again, it actually makes more sense to think about 91 before you think about 90, so we'll go ahead and do that. So it says ball B takes 1 second to hit the ground. And the question is, how long does ball A take? Well, again, you can think about it in terms of a kinematic equation, so I'll do both. But we have this right here. They both start out with an initial y velocity of 0, so that goes away. And I can rearrange to solve for time, so 2 delta y a y square root. And you can just say, okay, if I double this, if I double delta y, what's going to happen here? Well, I double delta y, you basically make this whole side the square root of 2 bigger. So to compensate, the right side has to be the square root of 2 bigger. So if this is 1 second, making it square root of 2 bigger is about 1.44 or 41 seconds. And you get that. If you don't like that, again, just make up numbers, right? If you don't like that, just make up numbers. Now, the issue is that there's with the whole make up number thing, is that you know to be something fixed. So if you plug in things here, it's not going to necessarily work. But you could, of course, just solve numerically for what delta y has to be, because you're given the information about the 1 second thing. So you could go back in here, plug in 1 second, solve for what delta y is. It's a pretty easy problem to find that delta y has to equal 4.9 meters, negative specifically. So then you can just use that negative 4.9 meters into here, but double it. So delta y is negative 9.8 meters to find the time for A. And if you do that, you'll find it has to be 1.41 seconds. So the answer here is C. And that's obvious, again, if you think about it from a projectile motion problem. Things aren't moving at a constant velocity on the way down. If things were moving at a constant velocity on the way down, then doubling the distance would double the time. Just like you're moving 60 miles per hour, you double the time, you move twice as far, right? But here we're not moving at a constant velocity, we're accelerating. So with that, each period of time we move a greater distance. So it doesn't take an entirety of 1 second to get to the next place. So there's a couple ways to think about it. For 90, it says ball A lands right here. Where does ball B land? Well, they're both moving to the right with the same speed. Again, if it helps you, make up a number. Say they're both moving to the right at 1 meter per second. So if this is in the air if ball B is in the air for 1 second, and ball A is in the air for 1.41 seconds, you can calculate that this has to be 1.41 meters, and this has to be 1 meter. 1 meter is obviously not half of that, so the answer is some, what does it say? A, I'm having over edge of the table, not necessarily half the distance, yeah. All right. Yeah, okay. And obviously eliminate the ones that don't make any sense. Like D and E or C, really. Narrow it down to only 2 that make sense. But I'll pause there for questions.